Hi, good morning. In today's lecture, I'm going to go ahead and begin with the next very important topic, very important from exam point of view, which is called general equilibrium. Now, when it comes to general equilibrium, from variance, there are three main chapters that you have to go ahead and cover. So again, this depends on the, as I was mentioning yesterday also, on the edition of which variant book you're following. If it is a 2008 edition or the 8th edition, then in that book, this is going to be chapter 31, 32, for your if you have to go back and if you have to map, then based on that, for us also, if you go to the variant folder, chapter 31 to 33 is what we are going to go ahead and cover in the coming classes. I'm going to do some of the advanced concepts here, and the basic concepts would be available in this folder. Okay. Now, to begin with, let us go ahead and understand one of the very basic terms called Pareto efficiency. What is Pareto efficiency? See, to understand Pareto efficiency, understand that I am going ahead and talking about an economy that has two individuals. Each individual enters the market with two goods. This is called the endowment of the individuals. For example, individual A can enter with 5 units of good 1, 5 units of good 2. Individual B can enter with 7 units of good 1, 7 units of good 2. It may not even be equal. Individual A could have entered with 0 units of good 1, 10 units of good 2. Individual B would have entered with 10 units of good 1, 0 units of good 2. It can even be non-symmetric. For example, A can enter with 1 unit of good 1, 4 units of good 2, 5 units of good 1, 3 units of good 2, anything. But the individuals are entering with the market with two commodities, good 1 and good 2, in certain amount. Now, the endowment of the individual is helping these individuals to earn income. So the concept here is that individuals do not have any income. When they enter the market, they sell this endowment, they use this endowment to earn income. This is what the concept is. Now, once the individuals have entered the market and have earned this income by selling the endowment, they can use that income to buy goods from the market. Which goods will the individual buy? The same goods. Good 1 and good 2. But they may not buy the goods in the same amount with which they entered the market. So, for example, individual 1 would have entered the market with 0 units of good 1 and only 10 units of good 2. But once he's exiting the market, he may exit the market with, let's say, 3 units of good 1 and 4 units of good 2. So, once the individuals have earned income, they will go ahead and buy these goods in some other amount. This can be found by using a concept of competitive equilibrium, about which also I will talk in detail. So we can find this concept using competitive equilibrium. But let's first understand what is Pareto efficiency. Pareto efficiency basically says that you cannot make any individual better off without making the other individual worse off. So let's write down the definition first. Pareto efficiency. Very, very important concept. You cannot make one individual better off without making the other individual worse off. If you're able to do that, if you're able to make one individual better off without making other worse off, so if there is a point from which you move to another point such that A is better off and B's utility is unchanged, or you have a point from which you move to another point such that A is better off and B is also better off. If that's the case, then this very point is called a Pareto superior point, or the better word is actually Pareto improvement point. The other point becomes superior. So it's a Pareto improvement point. You can improve over that point. However, if there is a point from which you move to the other point, and here when A becomes better off, B becomes worse off. B's utility decreases in order to increase the utility of A. Or there is a point from which you move to the other point in which A becomes worse off in order to make B better off, which means B's utility increases from this point to this point, but A's utility decreases. Then these points are called Pareto efficient point, because they were efficient enough. When you moved away from that point, you could make one individual better off only at the cost of the other individual. You could make one better off only at the cost of the other. So they become Pareto efficient point. All throughout, our aim would be to find all the Pareto efficient points. That is what my aim is. And once we have joined all such points, if we have more than one point on my box, if we join all such Pareto efficient points, then that is called a contract curve. So what is a contract curve? A contract curve, you can write down, is a set of points that are Pareto efficient. Alternatively, you can also say it is a locus of all such points. You can, when you join all the points, the curve that passes through all the Pareto efficient points, the line that passes through all the Pareto efficient points, that very much is known as the contract curve. So what is a contract curve? It's a line or a curve that joins all Pareto efficient points. Now, the point here is that where are these points really allocated? Where is this point, this point, this point, this point? Where are these points? So to understand that, we need to understand the concept of an Edgeworth box. It may not be a box. Box means it can be a rectangle, can be a square. So in that sense, it can have any dimensions. Now, when we talk about an Edgeworth box, the question is, what is it? Basically, this box is formed by considering all the endowments of the two individuals. So if I consider the endowment of the two individuals together, then what I receive is called an Edgeworth box. Take an example for this. So for example, individual A has entered the market with 0 units of good 1 and 10 units of good 2. B has entered the market with 10 units of good 1 and 0 units of good 2. How much is total good 1 available in the market now? 0 plus 10, 10. How much is total good 2 available in the market? 10 plus 0, 10. If I plot these dimensions, 10, 10, then what I am plotting would be an Edgeworth box. So how will I draw Edgeworth box? I will take my x-axis to be 10. I will take my y-axis also to be 10. This would be a straight line, please. And I will just join this. This will be 10. And this would be my Edgeworth box. So to plot the Edgeworth box, I would go ahead and understand what is the total amount available in the market with the help of all the endowments of the two goods or the two individuals. Now, let us go ahead and take an example. So this is example 1. We'll do many such examples. My utility function that I am taking is x, y. Now, since there are two individuals in the market that I have begun with, please understand that my utility function will also have two individuals. So this is the utility function of individual A. And I have to simultaneously draw the utility function of individual B, x, y. Also, when you write this x, y, you should clearly mention xa, ya, xb, yb. This helps you understand that this is completely individual A and this is completely individual B. That's the first thing. Second thing, you must also understand that when you talk about these individuals A and B, you must know what the endowment is. So I give you an example initially that endowment of individual A is 0, 10 and endowment of individual B is 10, 0. So what we can go ahead and do is that we can build an Edgeworth box out of it, which would be 10, 10. And I'll have 0, 0 here. And this is 1 unit of good 1, 2 unit, 3 unit, and so on. This is 10 units of good 1. This is 1 unit of good 2, 2 unit, 3 unit, and so on. And this is 10 units of good 2. And now, even if you don't consider this line, just tell me what this point would be. If you go ahead and make, if I ask you what will be the coordinates of this point, clearly it would be 10, 10. Right? So just imagine this. If I ask you to plot something on the XY axis, and I ask you plot the point 4, 5. How do you plot that? You go 4 here, you go 5 here, and this is your point 4, 5. Similarly, if I'm asking you to plot 10, 10, what would that be? You go 10 on the x-axis, 10 on the y-axis, and you get the point 10, 10. Now, that is what I had actually joined to build my Edgeworth box. So here I don't have any amount of both goods. Here I have maximum amount of both the goods. This is 10 units of good 1 and 0 units of good 2, which is nothing but the endowment of individual B. This is what individual B entered the market with. This is 0 units of good 1, but 10 units of good 2. So this is nothing but the endowment of individual A. He entered the market with 0 units of good 1 and 10 units of good 2. Now, I also go ahead and introduce the origins of the two individuals. Individual A's origin for the purpose of all indifference curve would be this. Individual B's origin for all indifference curve would be this. Now you might think, if the endowment is here and here, why are the origins here? Well, the origin is used to plot the indifference curve. The endowment is used to calculate income of individuals. So it's like this. Imagine individual A just like the usual x-axis, y-axis. And because his preferences are well defined, this is a Cobb-Douglas indifference curve because it is x, y, right? So what is a Cobb-Douglas indifference curve? We know x to the power alpha, y to the power beta. This is a well-defined indifference curve where alpha and beta can be anything. So if alpha and beta are 1, I get x into y. If alpha and beta are half, I get x to the power half, y to the power half. I could very well rewrite this as alpha log x plus beta log y. This is also well-defined preferences because this is just a monotonic transformation. So if my utility function is x to the power alpha, y to the power beta, I can have another utility function which is saying that take log on both sides. So log of x to the power alpha, y to the power beta. This is log of x to the power alpha plus log of y to the power beta, because this is just log mn. So it will be log m plus log n. This is nothing but alpha log x plus beta log y. And log of u is nothing but a new monotonic transformed utility function, v. So, my well-defined preferences, x to the power alpha, y to the power beta, can also be represented by alpha log x and plus beta log y. That's also possible. It could have also been represented by u is equal to x to the power alpha, y to the power beta. So e to the power u is equal to e to the power x to the power alpha, y to the power beta. And e to the power u would have been v. So v is equal to e to the power x to the power alpha, y to the power beta. Anything, any monotonic transformation is also well-defined preferences. This is 2x to the power alpha, y to the power beta is also well-defined. Anyways, let's come back to the point. So I know that this is a well-defined preference. And for a well-defined preference, my indifference curves are like this, right? They are rectangular hyperbolas. And I know certain properties about these indifference curves. What are the properties? I know higher the indifference curve, the more the utility. I know there is diminishing MRS of these indifference curves. I know they have monotonic property. Higher the indifference curve, more the utility. I know that they follow transitivity. I know they follow reflexiveness. We know all these properties, right? So we understand that for individual A, the origin is like this. Now, imagine another individual B. He also has this x-axis and y-axis. His preferences for us in the simplest case are also well-defined. It may have been well-defined, may not have been well-defined. But for our case, these preferences are well-defined. So what I go ahead and do, okay, because the preferences are well-defined, his indifference curves are also rectangular hyperbola. Again, higher the indifference curve, better it is. But now, if I have to combine this part of individual A with individual B, how do I go about doing that? It is an impossible task. I cannot just put one indifference curve over the other. I cannot just, have the same axis. So what I go ahead and I do is I start rotating this. So I have this and I just rotate this curve, this part of the curve, such that I have this on the other side. This is what I'm doing. So I am going ahead, I am rotating this, I am flipping this such that this individual B's curves appear like this. So this becomes the axis of individual B. And then I do exactly same thing, X here and Y here. So I am just going ahead and flipping it. Imagine that, you're going ahead and you're flipping it. Everything is changing and going to its diagonal side. So it's like this. If I have this, then OB goes on the opposite side and comes here. X goes on its opposite side and comes here. Y goes on its opposite side and comes here. Because of which, what really happens is that I just get a curve like this. This is what I have done here. And now, because when I was having this as my origin, for any individual, the indifference curves were like this. They were, higher the indifference curve. The more away they were from the origin, the more was the utility. So what I go ahead and I do is I make these indifference curves and I say the more away they are from the origin, the higher is the utility. So, this IC3 has more utility than IC2, has more utility than IC1. This is what we have done here. Now, once I have, individual 1 or A and individual B, I combine these two together. So what I do? I get this for individual A. Just the opposite of it becomes individual B. I draw the indifference curves of individual A like this. And with another color, let me draw the indifference curves of individual B. The direction of preferences for individual B is this, because you're going away and away from the origin. The direction of preferences for individual A is this, because you're going away and away from the origin. This is what constitutes the Edgeworth box. So origin is used to plot the indifference curve. And here this is telling me that, okay, this is the origin. The indifference curves are plotted away from the origin to show higher preferences. This is the origin. The indifference curves are plotted away from the origin. Now, once we have understood endowment, origin, Pareto efficiency, I am going to combine everything together. So what do? We say, okay, let's talk about Pareto efficiency. Only in the first example that I am taking, I am doing it number by number, each numerical number. From the second example, I will show you more of a economic diagrammatic approach. So we'll take the first example and go thoroughly with it. You should go ahead and do at least 5-6 examples thoroughly before you follow the approach that I will follow from the next example. Let's see here. See, let's take individual A or 1. Let's take individual 2. I'm taking utility of individual 1, utility of individual 2. And what I'm going ahead and doing is I'm taking various points in my Edgeworth box. So I understand that this point is 0, 0. This point only has good 1 in it. So this will be 0, 5, 5, 0. This point would be 10, 0. This point only has good 2 in it. So, because it is half of it, this will be 0, 5. This would be only good 2 in it. So 0, 10. This point somewhere here has both goods in half amount, 5, 5. Consider this point. This point means that, I have 10 units of good 1 and 5 units of good 2. That is what this point represents. So this will be 10, 5. This will be 10, 10. This would be, let's say, it has 5 units of good 1 and all units of good 2. It's like this. 5 units of good 1 and all units of good 2. So this point is 5, 10. So I'm taking some reference point. Doesn't mean you cannot take other points. These are just some of the points. All these points that I have taken are from the point of view of individual 1. These are individual 1's reference point. Please understand. not individual 2's reference point. I haven't done anything for individual 2 yet. So let's write down all the reference points of individual 1. He can have no unit of both the goods. He can have 5 units of good 1, 0 units of good 2. He can have 10 units of good 1, 0 units of good 2. These are the points. This. He can have 0 units of good 1, 5 units of good 2. 5 units of good 1, 5 units of good 2. 10 units of good 1, 5 units of good 2. He can have 0 units of good 1, 10 units of good 2. 5 units of good 1, 10 units of good 2. And 10 units of both. This is what his points can be. He can have anything. Once he has entered the market, he can have any of these points. Anything which is within the Edgeworth box. Now I have a question before I even go into this. See, when he entered the market, he entered with 0 units of good 1 and 10 units of good 2. And now I am telling you that he can have any of these points. Any of these points. Well, how? How are we telling that any of these points is something which would be affordable to the individual? How are we going ahead and telling this? If he is entering the market with this, zero units of good 1, 10 units of good 2, how is it possible that he can have both 10 units of good 1 and good 2? How can he have that much more income so that he can, this would be the best thing for him, that have everything of all the goods. But how would it even be possible that he can do that? The answer is that I am not yet bringing competitive equilibrium into picture. I am not bringing that. I am not bringing the concept of what is affordable. Affordability is not what I'm bringing into picture. I am just going ahead and talking about the efficient points. What does this mean now? This means that, look, when I talk about indifference curves, as an individual, you will always say, I want to go on the highest indifference curve that is possible. That is your preference. Your preference is always towards a higher indifference curve. But once you introduce the budget line in it, then you tell me what is affordable. Right? Because once you bring in the concept of income in it, then you think that, okay, I want this bundle, but I cannot afford this bundle. I can only afford this. So what you have to understand is that when we start building blocks, when we started with the very basic consumer theory also, we were not asking what is affordable. This never came into picture. We were just asking, how do you define your preferences? That was what was important. Of course, once you have defined these preferences, that will be my next question. Out of those preferences, which bundle can you afford? That is what is the concept of competitive equilibrium. When you go ahead and you join market, market means price of the commodities with preferences. But you are not talking about this at all. I am not bringing this concept at all into picture. What am I saying? I am saying, okay, to begin with, I just want my efficient points. Then after my efficient points have been released, I will go ahead and ask what are the points which are competitive. That is the next thing that I want to do. So do not get confused. Don't think about what is affordable currently. Don't talk about that. Just take all type of possible different points which are within your Edgeworth box. Find out Pareto efficiency. Then we will talk about competitive equilibrium also in the next part. We'll talk about that. Don't worry. Now, let's take this forward. So see here. See, when individual 1 has 0 unit of both the goods, and I know that the total amount available in the market is 10 units of good 1 and 10 units of good 2, then individual 2 will have all the goods. Right? So 0, 0 is a point which is here. Notice. But this 0, 0 is the farthest away from the origin of individual B. So this is where individual B will have 10, 10. Because for individual B, this is 0, 0. Here he doesn't have anything. So for individual B in the background, when individual A has 0, 0, he has 10, 10. So what am I doing? I am looking at the total amount available in the market, which I found by adding the endowment of the two individuals, out of which I am subtracting what individual A has to understand what is left for individual B. Let's do this process further. So total is 10, 10. Individual A has 5 units of good 1, 0 units of good 2. So B will be left up with 5 units of good 1 and all the 10 units of good 2. Just fill this up quickly. So then 10, 0 will mean 0, 10. 0, 5 will mean 10, 5. Always remember the sum should be 10, 10 because that is what will be a point in my Edgeworth box. Total should be always 10, 10. That is what my Edgeworth box will always represent. So just fill this up quickly. 5, 5 will have correspondingly 5, 5. 10, 5 will have 0, 5. 0, 10 will have 10, 0. 5, 10 will have 5, 0. 10, 10 will have 0, 0. So 10, 10 is this point for individual A. He is the farthest away from his origin. So which means that individual B will be at its origin and he won't have anything left with him. You must first of all learn to make this table. This is important. This is the basic building block of this chapter. You have to understand how to prepare this table. Now, let us go ahead and talk about the utilities of these individuals. To understand the utilities, we know that utility for individual 1 or A is given by his X into Y. And utility for individual 2 or utility for individual B is given by his X amount into Y amount. In this case, individual A has 0 amount of good X and 0 Y. So 0 into 0 is 0. 5 into 0 is 0. 10 into 0 is 0. 0 into 5 is 0. 5 into 5 is 25. I'll just keep drawing these lines for easy understanding. 10 into 5 is 50. 0 into 10 is 0. 5 into 10 is 50. So 0, 50 and 100. Let's just minimize this a bit. Similarly, find the utility of the other individual quickly. 100. 5 into 10 is 50. 0, 50, 25, 0, 0, 0, 0. Have a look. Just see if it is correct. Anything wrong that we have done. Now, once you have found this, let's revisit what was Pareto efficiency for us. When I go from one point to another, when individual A's utility increases, utility of B should decrease. Or when A's decreases, then B should increase. Then it is Pareto efficient. If A's utility is held constant and you are able to increase the utility of B, then it is Pareto improvement. It is not efficient. So let's start considering some points. Consider this. When I go from this point to this point, then utility of individual A is constant. It was 0 here, 0 here. But utility of B is increasing from 50 to 100. So from this point to this point, utility of A is constant. Utility of B is increasing. This point definitely is not a efficient point. It's not efficient. So we can cancel out this point. This is not an efficient point. Sorry. We can say that this is not efficient. Now take the next example. Start doing this for all points. Consider this point. When I go from this point to this point, A's utility is held constant and B's utility increases to 100. So this is also not efficient because I'm able to increase the utility of B without changing the utility of A. So this is not efficient. So we cancel out this point. Try for the next part. Is it efficient or is it improvement point? Check it. So utility of A is unchanged when I go from this point to this point. Utility of B is increasing. So even if you're able to find one point where utility of one individual is not changing and others is increasing, it becomes a Pareto improvement point. So this is not efficient. Now, consider this point. Can you find any point where one's utility is increasing without decreasing the utility of the other? Just check. Is there any point where you are able to improve the utility of both the individual or at least one individual? Let's check this out. So if I go from 5,5 to this point, utility of individual 1, that is decreasing, but utility of individual 2 is increasing. So utility of individual A is decreasing. Utility of individual B is increasing. If I go from this point to any other above point, utility of A is decreasing because A has more utility. It's greater than 0. If I compare this with any other point below, then here utility of A is increasing, but here in all these points, utility of B has decreased. So which means that you cannot find any point such that utility of both the individuals is increasing simultaneously when you move away from this point. This point is called a Pareto efficient point. Okay. Similarly, if you take this point, you will not be able to find any point such that you are able to increase the utility of one individual without decreasing the utility of the other. This is also a Pareto efficient point. Similarly, this is also a Pareto efficient point. When you move away from this point, then utility of individual A is definitely decreasing. Move to any point above. A's utility is definitely decreasing. So you will have to decrease the utility of A in order to increase the utility of B. So this is also a Pareto efficient point. So what have we got? We have got that this is Pareto efficient. This is Pareto efficient. This is Pareto efficient. When you join all such Pareto efficient points, what you get is called as the contract curve. So the set of all Pareto efficient points joined together is called the contract curve. Now, see, it is very difficult for you to every time go ahead and make these numbers. Although I want you to make this table at least for the next 7 to 8 questions that I do. I want you to go ahead and make this table every time and try it every time. But there is another approach which is a simpler one. So, which will come with practice, of course. So take this example. I draw this Edgeworth box. This is origin of individual A, origin of individual B. And what I do is I make an indifference curve of individual A. And I make an indifference curve of individual B. And I take a point here. Let's say this point is alpha. And I ask the question, is alpha Pareto efficient? Just think about this and tell me, is alpha Pareto efficient? Well, we can solve this problem in the following way. Let's hold utility of individual B constant. I am holding utility of individual B constant, which means I will be on the same indifference curve for individual B. And now I am asking, which is the highest indifference curve that individual A can attain? So can individual A go higher? Let's see. Yes, individual A can go to a higher indifference curve. If I take individual A to a higher indifference curve and look at this point, beta, then at beta, individual B is on the same IC because he's on that same blue curve. But individual A has been able to go on a higher indifference curve and has been able to increase the utility because he is going more away from the origin. Again, can individual A go even higher? Yes. How about this point? maybe gamma. B is on the same indifference curve, but A is able to attain a higher indifference curve. How about this point? Let's say theta. Yes, this is A, okay. A is able to go on a higher indifference curve. B is on the same indifference curve. So, because you could go from alpha to beta to gamma to theta, such that the utility of individual A kept on increasing without changing the utility of individual B. These points where you kept on increasing the utility of individual A were Pareto improvement points. You're able to improve, they're not efficient. But what about a point like theta? Is this Pareto efficient? The answer is yes. If I want to make individual A go to an even higher indifference curve, I will have to take individual B on a lower indifference curve. Individual B will have to go towards his origin. Otherwise, holding individual A's indifference curve at blue, individual, B's indifference curve at blue, individual A cannot go higher, cannot go in a region more than that. So we say that this is a Pareto efficient point. Ideally, whenever in an Edgeworth box, this is an indifference curve of individual A, this is the indifference curve of individual B, this is his origin, this is origin of individual A. Whenever this lens is being formed, whenever, then this lens actually represents a mutually beneficial area. What is a mutually beneficial area? Which means both the individuals will be better off in this region. How? Just think this. The more away I am from the origin, the better it is for individual B. The more away individual A is from the origin, the better it is. Individual A can go further away from his origin within this lens area. Individual B can also go further away from his origin in this lens area. So, A is able to increase his utility to a higher utility, and B is also able to increase his utility. If both are able to increase this utility, both are mutually benefited, which means that they have not yet achieved Pareto efficiency. They're still improving. There is a scope of improvement. But the movement, this lens shape area is zero. There is no area left in between, something like this. Completely exhausted. There is no lens shape area in between. You have attained this point right here. Then this is a Pareto efficient point. Because now, if individual A wants to go further away from the origin, B will have to go, towards his origin. He will have to reduce his utility. So, for well-defined preferences, we found out that the Pareto efficiency is defined where ICs are tangent to each other. Because when they are tangent, my lens shape area is not there. Lens shape area is 0. So there is no mutually beneficial area left. Then in that case, to increase the utility of one individual, you will have to reduce the utility of the other individual. So it's a Pareto efficient point now. The question is, how do you write this mathematically? Very simple. What does tangency mean? We know that tangency actually means that the slope are equal. Slope of what? Slope of indifference curve. They are equal because they are tangent. What is the slope of indifference curve? We know it is marginal rate of substitution, MRS. So because at Pareto efficient points, the indifference curve of A and B are tangent to each other. We have exhausted that length shape area. We are saying that the slope of indifference curve of A is equal to the slope of indifference curve of B. This is what is meant by tangency. That MRS A is equal to MRS B. And in the background, we know MRS is nothing but MUX by MUY, MUX by MUY. So this is MUX of A is equal to MUX of B. This is what is the equation of contract curve. Because it is the contract curve that was showing me Pareto efficient points. And Pareto efficient points in our case is given by the point where MRS are equal. So therefore, because of these two things combined together, I have this as the equation of the contract curve. Now, the utility function of individual A was XAYA. What will be MUX? Very simple. How utility changes when X changes? Differentiate this function with respect to X holding Y constant. So Y is a constant. And differentiation with respect to X will be 1. So it will be 1 into Y. What will be MUY? How utility changes when Y changes? Holding X constant. So you know this would be here Y is held constant. So this will be XA. X is a constant. And what will be MRS of individual A? It will be it would be YA by XA, because this is MUX by MUY. Similarly, if I ask you what is the utility of individual B given by, you will say XBYB. What is MUX? How utility changes when X changes? Holding Y constant, so Y is the constant, it will come out. And differentiation with respect to X will be 1. MUY, how utility changes when Y changes? Holding X constant, so it will be X. B. MRS of individual B will be YB by XB. So if I ask you, what is the equation of contract curve? Well, we know that contract curve was all Pareto efficient points. And Pareto efficient points were where tangency was met. Indifference curves were tangent. And they were tangent means their slopes were equal. So I have YA by XA is equal to YB by XB, which means my Pareto efficient points must meet the condition that YAXB should be equal to XAYB. This is the equation of contractor. So basically the ratio of y by x for individual A is equal to y by x for individual B, or the cross multiplication. Now, if you go back and check it in the table once, this was the table that we had. You can see this also, this cross multiplication also. So if I go ahead and I take the first point, let's consider here, what will be YAXB? So YAX will be 0 into 10, which will be 10. What will be XAYB? It will be 0 into 10. Sorry, this is 0, right? 0. This is also 0. So the two are equal. So yes, this has to be a Pareto efficient point. Now do the same here. What will be YAXB? It will be 5 into 0, which will be 0. What is XAYB? It is 5 into 10, which is 50. These two are not equal. So this is not a Pareto efficient point, this point. So we can use the equation of the contract curve. Again, here it will be Pareto efficient. 5 into 5, 5 into 5, 25 from both the sides. It will be Pareto efficient. This will be 5 into 10, 50, and 5 into 0, 0. They're not equal. So basically, what do we get? We get that only these 3 points will satisfy this equation that we just found out. So this becomes the equation of the Pareto efficient points. You can simply, when any point is given to you, suppose I say is 3, 7 and 7, 3 Pareto efficient. No need to do anything. Just put it in this equation and ask yourself the same question. So this is XAYA, individual A. This is XBYB, individual B. XAYB is 3 into 3, which is 9. YAXB is 7 into 7, which is 49. Since these two are not equal, it is not Pareto efficient. It's not a Pareto efficient point. Right? Now, if I ask you another question, is endowment Pareto efficient? What is endowment? Individual A started with the endowment 0, 10. B started with the endowment 10, 0. So this is XAYA, individual A, XBYB, individual B. And I understand that XA into YB is 0 into 0, which is 0. YA into XB is 10 into 10, which is 100. These two are not equal, so it is not Pareto efficient. This is usually a question that's asked in papers like JNU, paper like IGIDR, paper like SAU. Are these points Pareto efficient? Of course, it's not coming in DSE. It's very, very basic, very easy. What we have done today. You won't be asked, you won't be seeing this in DSE, ISI, of course. It can come in IIT JAM though. So, they will give you a point and they will ask you if that point is Pareto efficient. You just have to plug in those points in the contract curve equation that you found out and see if it is Pareto efficient. Right? Okay, fine. So we'll continue in the next class and I will introduce the concept of competitive equilibrium.